Right. The third part of NMR that's important is the integration trace. If we look at an NMR as it comes out of the computer, we see that the computer runs a pen over the top of each peak, and as it does so, it integrates the peak. And I'm sure people who know a bit of maths will know that integration measures the area under a peak. You'll be very pleased to know you don't actually have to do any integration in A-level chemistry. That's just what the computer does. And as it's passing each peak, the line, the trace on the graph or on the spectrum goes up in proportion to the size of the integration trace. So what you end up with is a series of lines on your spectrum which tell you the area under each of these various peaks. So in this spectrum here, I've got 4 different peaks. I know they're kind of split up into little bits, but we'll come back to that in a minute. I've got 4 different peaks, and the integration trace lines are telling me that they are in a 2 to 3 to 2 to 3 ratio. So without worrying about the particular bits and pieces of this molecule and what the other peaks are, just focusing on integration trace for the moment, what that tells us is the ratio of the number of hydrogens producing each peak. Number of hydrogens producing each peak. And I'll just pop that word relative . So as I said, we usually we've got some peaks here, whatever they are, and then we get this kind of integration line which scans across it and usually sort of goes up. In the old day, you'd have to actually measure these lines with a ruler or whatever it was, and then you'd get I don't know, 2.6 centimetres to 3.9 centimetres, and you go, okay, that's 2 to 3. You don't have to do that anymore. We'll give you the whole number ratios in the exam. So that tells me that I've got a ratio of 2 to 3 to 2 to 3 hydrogens in that molecule. Now, what does that mean? Well, if I've got 2 hydrogens generating that peak there, they must be in the same chemical environment. They must probably attach to the same carbon, right? So those 2 hydrogens are probably a CH2, and these 3 hydrogens are probably a CH3, and then I've got another CH2 there and another CH3 there. So whatever else is going on in the molecule, and there is other stuff going on, I can see that I've got those particular groups in my molecule, and that's hugely helpful in us putting our molecule together. So if we just take a simple example, if we take ethanol. So for ethanol, I've got 3 distinct environments for hydrogen, and we're in a ratio 3 to 2 to 1 in terms of the number of hydrogens in those environments. So in my spectrum, what I'd expect to see is peaks in a 1 to 2 to 3 ratio in terms of their integration trace, or in terms of the area under each peak. So where the single relates to an OH, and the 2 relates to a CH2, and the 3 relates to a CH3. Now, we just have to be a little bit careful, because I can have a molecule like this. We've seen this kind of example before, where we get a line of symmetry going through the molecule, and we know that in the spectrum here we will just get 2 peaks. because these two CH2s are identical and these two CH3s are identical. When it comes to the integration trace, the ratio will still be 2 to 3 because the hydrogens are in a 2 to 3 ratio. In other words, it won't say in the exam question won't say 4 to 6, it won't be helpful to you because we're looking at the relative number of hydrogen atoms producing each peak in each unique chemical environment. So we just have to be a little bit aware that we'll get a whole number ratio for the integration trace, which we might have to double or triple for our molecule. Obviously, it helps having the empirical formula. So if we knew, for example, that the empirical formula of our molecule was C4H10O, and we've got 5 hydrogens here, and there's actually 10 in the molecule, well then clearly I have to double that. It's really 4 and 6 to give us the overall numbers. Okay, so integration trace values are very useful, and we can put an awful lot together just from that. But even more useful than that is the spin-spin coupling. So spin-spin coupling takes place because the local environment of any hydrogen that is in the spectrum that we're looking at is affected by other groups around it. And we talked about how it's affected by electronegative groups or electro-withdrawing groups, which de-shield the hydrogen and shift it to the left of our spectrum, that thing called chemical shift. But as well as electronegative groups, there are going to be other hydrogens around. And the frequency of this hydrogen will be altered by the presence of this hydrogen because the hydrogen nuclei, the proton in there, acts like a tiny little magnet. And it can either be in line with the magnetic field, the applied magnetic field, or it can be against it, and that'll have a tiny little effect on the local field of this particular hydrogen here. So that's the first point. Any hydrogen in a molecule can be affected by hydrogen atoms on neighbouring carbon. So we're not interested in other hydrogens that might be here. Other hydrogens that are around the same carbon will be equivalent. This only happens for non-equivalent protons. In other words, if I had methane, the two sets of hydrogens here don't affect each other because they're all equivalent. So I won't get any kind of spin-spin coupling with those. But if I've got a different molecule, there's other stuff going on, and these are non-equivalent hydrogens, then they will affect each other. So our hydrogen here is affected by that hydrogen there. So let's just clarify, when I talk about the hydrogen here, this is the hydrogen that is producing the peak. And if there's one hydrogen, sorry, not one proton, one hydrogen on the neighbouring carbon produces two chemical environments, so with or against, so we get a split, so to slightly above and slightly below, to make two peaks. Usually called a doublet, and those peaks will be in a 1-to-1 ratio because we're going to get just as many protons, or almost as many, nearly 50% protons with as against the applied field. If there are two hydrogens next door, so let's stick another one on here. Well, of course, that can be up or down as well, but the picture's a bit more complicated than that because we've now got two, right? So they can both be against the field, or they can both be with the field, or one can be with and one can be against. But remember that, like tossing coins, two heads, two tails, head, tail, we also have tail, head. So I get three different environments for this hydrogen here, but they're in a 1 to 2 to 1 ratio. So I get three peaks, we call that a triplet, in a 1 to 2 to 1 ratio. So we'll often get this kind of thing on the spectrum. It's not always exactly 1 to 2 to 1. You can see there it's kind of the right shape. That's actually the same. That's a 1 to 2 to 1 ratio there as well. If I just fill this out and I put a third hydrogen on there, well, then things get very complicated because we've now got all of them against or all of them with, but we can have two with and one against, but there's three ways or three permutations for that, and then similarly we can have two with and one against, and there's three ways of doing that one as well. So we end up with four different peaks, and now in a 1 to 3 to 3 to 1 ratio. So four peaks, which we call a quartet, in a 1 to 3 to 3 to 1 ratio. That kind of thing. And if these numbers seem familiar, that's because you've probably seen them before. Sorry. 1, 5, 10, 10, 5, 1. There we are, in Pascal's triangle. So if we had 5 neighbouring protons, we'd get 6 peaks in a 1 to 5 to 10 to 10 to 5, 1 ratio. You don't have to worry about that. It's not on the syllabus. You just need to know these three scenarios. But the simple way of remembering it is the so-called n+1 rule. In other words, if I've got one hydrogen next door, I get two peaks, n+1. 2 hydrogens, 3 peaks. 3 hydrogens, 4 peaks. 6 hydrogens would give me 7 peaks, and so on. You get the idea. So if I look at a spectrum of ethanol, for example, okay, that's ethanol. We've got 3 peaks. Remember, we were talking about this earlier. They would be in a 1 to 2 to 3 ratio in terms of their integration trace. But we also see these splitting patterns clearly here. So for let's just finish this off over here. There we go. For the single H on the OH, that's there, which is coming in around about 4.5. Now the OH, the proton on an OH can vary an awful lot in where it appears in the spectrum. You'll see it anywhere from about 0.5 up to 5 in terms of its position. It depends on the solvent that's being used and so on. It gives you different positions. Also, interestingly, the OH proton doesn't split. It's not affected by neighbouring protons, presumably because it's hydrogen bonded and it comes and goes fairly readily and doesn't hang around long enough to create the coupling necessary. If we jump to here then, so this is our CH2. We know it's the CH2 because the CH2 is next to the oxygen, and that's shifted to the left to about 3.5, 3.6 there. And if we look at the pattern there, it's split into a quartet. So the CH2 is split into a quartet because it's next to 3 hydrogens. So the CH2 is next to 3 hydrogens, so the CH2 gives us a quartet. And then our methyl group down here, the CH3, gives us 3 peaks. So these 3 hydrogens here are split by the neighbouring CH2 group. So they give us a triplet. CH2 splits to make 3 peaks in a 1:2 to 1 ratio. So the confusion comes often where people see 3 peaks and think, well, maybe, oh, 3 peaks is 3 hydrogens. No, it's 3 hydrogens there because the integration trace ratio is 1:2 to 3. The triplet that we see there is because that CH3 is next to a CH2. Of course, anywhere we've got an ethyl group, we're going to get a CH2 next to a CH3 and a CH3 next to a CH2, which means we'll get a quartet of height 2 and a triplet of height 3. So we're going to see that quite a lot in various different molecules. This pattern, if there's a CH3 split by a CH2, there has to be a CH2 split by a CH3. It's a very common pattern to see on an NMR, and it's a good thing to pick up on fairly early. Also notice that I can't remember what I was going to say there. It's gone. Sorry. Is it going to come back? I don't know what I was going to say. Okay, I'm going to leave that there. Oh, I didn't. Right, yes, I remembered. If we have I didn't say, if we have a single peak that's not split by anything, that has a name as well. It's called a singlet. Okay, which means it has no splitting. So that's a singlet peak there, quartet, triplet, and a doublet if it's 2 peaks of equal height. All right, I'm just going to do one more little video on solvents and the reference sample, and then we're done with NMR.